By now, we should know how to factor quadratics, and we also know that factoring leads to finding the roots of the polynomial, correct? But by the end of this lesson, we shall learn strategies to find solutions to cubics, quartics, even quintics. The first thing to introduce is the sum and difference of cubes. The sum of cubes was in one of the exercises of the previous lesson. You can derive it by long division, but to perform long division, you still have to be able to know what the divisor is. So suppose that Alice marches into a test, eager to show her crush, Tom, that she can attain an A. She strikes through every problem as if she were breathing. The last question is simple, a factorization involving the use of the sum of cubes. But wait, there's more. Her mischievous brain of hers has forgotten the sum of cubes. How will she impress Tom now? You probably have gotten yourself into a similar situation before. When that happens, you do what a mathematician will do. You try to derive the formula on the spot. First, I ask myself, what is the unknown? Sure, I want to factor, but be specific. Can I factor completely, or do I just want to factor out? Factoring completely, if you're brave enough, you can try. But in most cases, when we factor, we do it step by step, taking the linear factors, meaning our final result will look something like this. So, first try checking what that will lead me to. It leads to x cubed plus x squared y plus xy squared plus y cubed. That's close, but not quite. I dislike the x squared y and xy squared. We made progress though. I can do two things now. The first thing is to continue the guess and check process, but with the knowledge we gained. Most people here can intuitively reason out, now one of the factors should contain a subtraction to remove the x squared y and xy squared. After a sequence of guesses and checks, you should be able to find that it can be factored into x plus y times x squared minus xy plus y squared. But here's another genial, slightly rigorous way to do it. From this equation, I can write down that x plus y times x squared plus y squared minus x squared y plus xy squared equals x cubed plus y cubed. This originates from the idea that instead of simply mentally noting a new discovery, you should express it verbally. It's like taking notes in class. Now the note can be elaborated by factoring, and suddenly the x plus y can be taken out as a common factor. It then simplifies to x plus y times x squared minus xy plus y squared. Isn't that amazing? That's one less thing you have to memorize. You see, there's virtually nothing that you have to retain. It's all about honing your creativity. You still have to be able to recall the occasional formula or theorem, but you can avoid memorizing most things if you understand the creative problem-solving techniques used to find them. And it's arguably better this way. You can apply the same techniques to solve analogous problems. This, of course, doesn't narrowly apply to math. Sometimes in your history class, you can predict what happens next from the preceding events. It's morally comforting as well. It shows that a piece of math truly is something you could have invented yourself if you had those techniques at your disposal. And the more you practice these techniques, the closer you are to becoming a mathematician. To take a step further, don't memorize the specific techniques used to derive something. Instead, carve into your brain the ideas and questions that were inquired to reach those specific techniques. Here, I asked myself, what is the unknown? And I had the idea to write down a note of progress. That note of progress led me to realize that I can elaborate on that note, factoring it down to the answer. I admit, you do have to memorize a crucial formula, like the quadratic formula at some point, just for the sake of times. But the sum of cubes comes easily to us because it will get ingrained into your brains once we use it enough times. It's often important that we reflect on what we've found. Can you use the result for an analogous, almost equally important problem? And in this case, we can use it to derive the difference of cubes. Here, I can use a technique called substitution. Let b equals negative x. And after finding its implications, we substitute the b in for x. We have a sum of cubes again, which we know how to factor. Now we just resubstitute. The golden rule for factoring advises us to always try, before anything else, to find the greatest common factor. If you see one, take it out. Then you can carry on with the rest of your repertoire of factoring techniques. Here are two more techniques you can use to factor. The first is what's called grouping. But really, grouping is factoring a common factor, but there's the added layer of needing to find a pattern amongst the terms first. So in this example, what's a pattern? The pattern is that if you take a look at the coefficients, it always begins with a number, then a doubled number. Then it's a random number again, then that number is doubled. We should always try to find a common factor, and although there isn't a clean common factor for every single term, there is for each pair. Take out the x to the fourth, negative 6x squared, and 5. Now I realize that I can factor a common factor again, with the x plus 2. Taking the x plus 2 out leads me to this expression. Grouping, as its name suggests, is to group the terms that follow a pattern. Then you can take a common factor for each group. Once you do that, you can factor for a second time. Here's the second technique for factoring: substitution. When I get here, I notice that this expression is very analogous to a quadratic. X to the fourth is just x squared squared. X squared is just x squared to the first power. Meaning, if I substitute some variable, let's say u, then I have a quadratic. I can then factor this quadratic and then re-substitute the x. Then we can use the difference of squared. X squared minus 1 is x plus 1 times x minus 1. And x squared minus 5 is x plus root 5 times x minus root 5. This is where the previous lesson comes into play. Synthetic division can be used to find factors of a polynomial. In synthetic division, we always get a remainder. But what if the remainder is 0? This implies that the thing we divide by is perfectly divisible, which then follows that this number is a root of the polynomial. Because of that, I can write down that the product of x plus 1 and the quotient is the polynomial. But now, notice that we can continue the factoring process, only focusing on the quotient of the synthetic division. I find that I can't use any factoring techniques here, so I retry this checking method, and as it turns out, 1 works, and therefore x minus 1 is a factor, implying 1 as a root of the polynomial. Now we have a quadratic left, which is factorable. So now we have a way of rapidly checking if a number is a root of the polynomial. Put the number in the synthetic division, and if it ends in 0, then the number is a root. That's cool, I guess. But Sota, you say, this is not a sustainable method. I won't conveniently have a list of numbers that could potentially be a 0 of a polynomial every single time. And yes, you are totally right. Or are you? You see, in every polynomial, there is a list of numbers that the 0 has to be in, given by the rational root theorem. Kinda. It only works for rational numbers, which are numbers that can be expressed as a fraction of two whole numbers. Basically fractions. Let's say that we have a quadratic. We don't know the x term, but we know the x squared and constant term. We can't factor it, but we do have an idea of what the factors may look like. For example, x plus 1 times x plus 3 is never equal to x squared plus kx plus 4, because the expanded form contains a 3 as a constant term. In other words, a times b has to equal 4. Now, we can take this idea further to a cubic. A times b times c has to equal this constant term at the end. The only possible way to form a constant term is the product of a times b times c, right? If you want, you can say that there is only one way to choose 0 x's from a total of 3 options. Actually, any number choose 0 is 1. That is to say, for any polynomial, whenever the leading coefficient is 1, the product of these numbers is equal to the constant term of the polynomial. So now we have a relation between the roots and the constant term of a polynomial. And what if the leading coefficient is not 1? It won't exactly work. For example, in a quadratic, if we have some 2x squared plus kx plus 4, then the factor form is never in this form. If it was, then it would lead to a leading coefficient of 1. So we divide the polynomial by its leading coefficient and we obtain the following. You're allowed to divide it because dividing an equation by a constant doesn't change its roots. Then the product of the roots with opposite signs is z divided by y. This is the intuition behind the rational root theorem. The rational root theorem asserts that if we have a rational root of a polynomial, then the root is always in the form p over q. P is a factor of the constant term and q is a factor of the leading coefficient. P and q are also integers and share no common factors. There's even the added restriction where the leading coefficient and the constant term cannot be 0, and where the coefficient must be integers. If you think about it, this isn't surprising. The product of roots with opposite signs always have to be d over a, so of course the rational roots have to be, well, factors. By the way, forget all of these restrictions. When I think of the rational root theorem, the only thing I think of is the p and how it's a factor of the constant term. Then, if the leading coefficient is not 1, I think of how p gets divided by q. It would make no sense to divide q by p. And we can omit that they are integers. Of course a factor is going to be an integer, that's what the definition of a factor is. It then follows that the coefficients have to be integers too. And be careful, when a theorem states a certain truth, then that truth can be true sometimes without an assumption made, for example, that the coefficients are integers. But the proof of this theorem cannot be proven so easily without making that assumption. So let's apply it to a problem. Here, if we have rational roots, aka fractions, then the roots will always be in the form p over q. The factors of 16 are 1, 2, 4, 8, and 16. The factors of 2 are 1 and 2. But keep in mind, factors can be negatives too, so we can put a plus or minus in front of the fraction. The fraction here is a list of all the possible rational roots of our polynomial. But it's not just a list, it's a complete list. If there's a rational root, it has to come from this list. Be cautious, however, since it doesn't consider irrational or complex numbers. If there's an irrational root, like the square root of 2, it won't be contained in this list. So let's test our list like we did earlier. You can do them in any order, but it's smart to do in an order like 1, -1, 2, -2, 4, -4, and then consider 1/2, -1/2 because fractions are annoying to deal with. After a couple of tests, I find that -4 works. So we can write that the polynomial is equal to x plus 4 times the quotient, 2x squared minus 5x plus 4. If what I had left was a cubic or some polynomial with a greater degree, I could try to use the rational root theorem again to find further zeros until I get into quadratic. But because all I have left is a quadratic, I can now factor it normally using the quadratic formula. And notice, we get complex roots, but they were and never will be contained in the list. You should think of the rational root theorem as a, quote, last resort in your factoring process. You first have to find all the possible values of p and q and then input that in your synthetic division. The other factoring techniques, by contrast, can be done in a few lines. The theorem is not even 100% reliable because, in this example, we had irrational and imaginary roots. Here's a proof of the rational root theorem. Let p over q be a rational root of the polynomial f of x with integer coefficients, where p and q are positive integers that share no common factor. Because p over q is a root, f of p over q equals the following, by the definition of a root. Then we multiply by q to the n. Subtracting dq to the n from both sides and then factoring the p out leads to the following. P is a factor of the left side, which means that the right side is also divisible by p. We have let p and q share no factor, right? So it has to divide d. That is, p is a factor of the constant term. The proof that q is a factor of a is a similar process. Subtracting ap to the n from both sides leads to the following. Q is a factor of the left side, implying that q divides a. And our hypothesis is proven. The rational roots of a polynomial truly are always in the form p over q. An analogous idea can be formed about the irrational and imaginary roots of a polynomial. As a student, if you toy with the equations a bit, you may come across something that doesn't make sense, a seemingly unreasonable contradiction. We know that the coefficients of a polynomial depend on the roots, right? Then how come we can have irrational or imaginary roots when the coefficients are rational numbers? The only way to answer this is to find a way to guarantee that every coefficient is rational even with irrational roots. In mathematics, we have something called a conjugate. The conjugate is where the famous difference of squares comes from. A plus b gets multiplied by a minus b to guarantee that we avoid an ab term. So the conjugate for an expression a plus b is a minus b. When 2 plus root 2 is multiplied by its conjugate, we end up with 4 minus 2. The root 2 disappeared. In a greater context of factors, the same thing happens. The roots get cancelled out. But if it was multiplied by anything other than its conjugate, we would inevitably have irrational coefficients. So whenever every coefficient of a polynomial is rational, the irrational roots must come with their conjugate pair. And in the same way, if every coefficient of a polynomial is real, then the complex zeros must come with their conjugates. Be careful when conjugating a number. Make sure to do this following exercise and check your solution, because you probably will make a mistake unless you're careful.